We're going to delve a little bit more into forces today. I'm going to describe a bit more about forces, and then we're actually going to start to do some Newton's second law problems today. Very important lecture, okay? Some of the stuff we're going to learn today is stuff that we're going to be utilizing for the rest of the class, really. But let's explore a little bit more about gravity. Now, we actually have an entire chapter on gravity that we're going to be covering a bit later on in the course. That's at the very end. But for now, I'll just describe to you some of the real basic stuff here. Gravity, of course, is a force, and we have a certain way that we describe that. Technically speaking, though, Newton's law of gravity is given by the equation at the bottom here. G M1, M2, where M1 and M2 are two masses that are attracted via gravity. They have a distance between their centers, which is r squared. By the way, distance between centers, not from their surfaces. It's from the center of the objects. Capital G is the gravitational constant, has a value of 6.67 times 10 to the minus 11, and it's just a constant. Okay. Now, when an object has a force of gravity exerted on it, you can, you could use this formula, but you're not, because this is a little overkill. You don't need to do all this stuff. When we want to apply this to objects that are on the ground or close to the ground, one of the m's becomes the Earth's mass. The other m becomes just the mass of the object that we're interested in. And if we're talking about the distance between the two objects, well, if we're close enough to the ground, we can simply approximate that to be the radius of the Earth. So the force of gravity ends up taking on this appearance right here, G capital M little m r squared, pointing straight down. But check this out. There is the G, the capital M, and the r squared. Those are all effectively constants. Mass of the Earth, radius of the Earth, gravitational constant. So this thing can be rewritten, and we combine the capital G, the capital M, and the r squared all together, and that's what our little g is. 9.80 meters per second squared is the value that we're going to use. So every time we have a force of gravity that we work with, we can replace that with mg when we're doing our calculations. Okay. And again, this assumes that we are, close to the ground, on the Earth, all that good stuff, right? Okay. So, anyway, this stuff is all a constant here, and it takes the form, if you look, this formula takes the form of ma, Newton's second law, mass times acceleration. And so we interpret the G capital M r squared as an acceleration, and thus it is 9.80 meters per second squared. All right. So in my free body diagrams, I'm going to draw a force, and I'm going to say Fg. But then when I write down equations to solve things, I replace Fg with lowercase mg, mass of the object, gravitational acceleration. Fantastic. Well, look at that. I just said it. Just said it. Right here. Right here. There it is. Now, what's interesting about this actually is the following. If this is the only force that acts on the object, okay, let me show you this, right? If this is the only force that acts on the object, Fg, right, then that, according to Newton's second law, equals ma. Right? Now, what's interesting about this is we can change this right here, G, M, little m, r squared, ma. Now, here's what's interesting, is that, no, it's different. The capital G and the capital M is not the same as a lowercase g, lowercase m. Capital G is a constant. The big M is the mass of the Earth. But when I write this out here, gravity equals ma. That's Newton's second law. And I write what gravity is, G capital M little m over r squared. You'll notice this. The force of gravity The force of gravity depends on the mass of the object, but so does the acceleration, such that they cancel out, and we see that our acceleration, which is what we call g, come on, which is what we call g, it has this form up here. And that's why we're able to know that all objects will fall at this rate regardless of their mass. Because again, the mass determines gravity, but also determines your acceleration. So those effects cancel each other out, and that's why we're left simply with g. Okay. A little too much going on this slide here. All right, so the first set of problems that we're going to work with are problems that are, as easy as we can get. Equilibrium problems. Equilibrium problems. And we learned about equilibriums last time. There's a static equilibrium where the object is at rest, and there's a dynamic equilibrium where an object is moving at a constant velocity. The condition for equilibrium is that all of your forces in the x direction must sum to 0, and all of your forces in the y direction must sum to 0. And if you happen to incorporate a z direction, you'll need to do that as well. Okay? This is all based on Newton's second law. I abbreviate Newton's second law a lot of times N2L. And N2L says that for conditions of equilibrium, the summation of forces equals ma. But if a is 0, then this equals 0. And in order for a vector to be 0, all of its components must add up to 0. So that's what we mean when we talk about the condition of equilibrium. We look at a situation, we analyze all the forces that act on the object, and we have to sum their forces, and it must equal 0. And then we know the object is in equilibrium. That's the condition for equilibrium. And I just ruined this thing. Okay. So I have a question for you. There is a vehicle here that is being pulled to the right with, I don't know, something, rope. Which is the correct free body diagram for the car? A lot of C's, a lot of C's, a little bit of B. Gotta tell you though, I'll be honest, I'm not a fan of C. Not a big fan of C. Is somebody else not a fan of C? No, they don't care for C too much? If that's the case, anybody want to tell me why they don't like C too much? What's wrong with C?
Wouldn't there be no kinetic friction since the tires would be moving too? So there's
you don't need
nothing
to
like
get into that.
going
We don't
backwards.
it's not that important. That's not really it. There's something else going on here. I mean, we don't have to identify any of the forces yet. No, the resistance is okay. Nobody knows?
Because there's nothing pulling the car back away from it?
No, that's not it. All right, let's talk about it.
Okay.
All right, we're going to learn something. Are you excited? Buckle up. We're learning. Brandon. The speed is constant. This car is in dynamic equilibrium, which means the summation of forces in the x and y directions need to sum to 0. There's a problem with C. C shows a net force to the right. C is indicating an object that is accelerating, and this car is not accelerating. B is wrong for the same reason. B is wrong for the same reason. Now, the answer is either A or D. It can't be A. Actually, it could be A. It could be A. I don't think you should say A. You should say D, but I wouldn't fault you for saying A. Put it that way. Because what's down? Gravity, right? What's up? Normal force, probably. And then, does there need to be forces in the x direction? Probably, but not necessarily. You just need F net being 0. I mean, it's possible this tension here is just slack, right? It's just completely it's not. I mean, the car is just. I mean, because you don't want to use a rope to pull a car, right? because good luck stopping at the stop sign or at the stoplight. That's not going to go well because there's nothing to slow it down. D is right because we would say that there's tension to the right. And then to the left would be probably some kind of friction, static friction probably. Yeah, static friction, I would guess. So, not kinetic though, not kinetic. And this is a little tricky when it comes to vehicles, but the condition for whether you consider something to be static or kinetic is that if it's kinetic, then at the point of contact, the surfaces need to be moving relative to each other. That doesn't occur for tires, though. Okay, if this car skids, that's kinetic friction. You hit the brakes really hard and the car skids. So it's moving relative to the ground. It creates maybe a little bit of smoke. That car smell gets into the air. And that would be kinetic friction, but otherwise it's static friction. Because again, the tire doesn't move relative to the ground. When it comes in contact with the ground, it doesn't move relative to the ground. It's the same reason for walking. When you walk, what propels you? Static friction. Static friction propels you. Okay, if your feet were moving relative to the floor, that's called slipping. People don't walk too well that way. So, little detail, but important. So anyway, we don't have to identify the forces here, but I'm assuming that this has tension in it. And if it does, the answer is D. And then we can talk about what could this be, this force going backwards. Could be kinetic friction, could be static, it could be air resistance, it could be, I don't know, anything, a lot of things. All right, car is parked on a hill. What's the correct free body diagram? C, huh? C, huh? Well, I think I might like that, actually. Yep, it's C. So why are the other ones wrong? A doesn't have any forces in the x direction, and in fact, A is telling us that this car is actually accelerating down the ramp because there is a net force in x here, right? The little component here, a wee little component, but it's there, and it would cause the car to accelerate down the ramp. B's got a force going down, which again, net force is not zero here. This car is doing the same thing as A is doing, except it's moving a little faster. C works. D is just, I don't even know what's going on with D. D must stand for drunk because whoever came up with that was drunk, and it wasn't me. So it just is wrong. I mean, like, there's no gravity vector. I suppose you could, I mean, D is like C, but they took the gravity vector and they put it in components, which you don't do. When you draw free body diagrams, you don't draw components. You draw the standard vectors. The component stuff is worked out in the equations. So, any questions about this one?
When we're doing, or when we're drawing something like this, are we going to be putting the XY axis according to the horizontal platform? Like, you see how the graph tilted?
Yes, if the picture's tilted, you're going to want to make your coordinate system tilted.
Okay.
Because there's several reasons for this. One, it will make your mathematics easier. Notice in C, two of the vectors are along the axes, so they don't have, components, x and y components. Only gravity has an x and y component. So from a mathematical standpoint, your life's a little easier. But here's the other issue. If the object does accelerate, you need to know the acceleration along the direction of motion. If you did not tilt the coordinate system, you're going to have the acceleration in terms of a direction that the object is not moving in, which means you're going to have to take that acceleration and put it in components in terms of how it is moving. So you're creating yourself a nightmare here if you don't tilt the coordinate system. Okay, let me just put it this way. If you don't tilt the coordinate system, I would be quite shocked if you get the problem correct. I will be very surprised. And then after you get the problem correct, I'm going to be like, did you not feel like you wasted your time? And you're going to be like, I think you were right. I think you were right. I'll never do that again. Okay. And then we high five, but not really because I can't touch you. So we just air five. And then we go on with our day. The answer is not D because they're not properly displaying gravity. It seems like D is trying to take gravity and split it into components, which is a big no-no. Don't do that. Okay. All right. Anything else? Okay. Yes, we would call this force going up the incline static friction. Static.
Real quick,
Yes.
what if C had also the D vector going down? What would
Would be
that
going
mean?
down.
Like you see the D vectors going down the Y.
I don't know what that would be. I would have no idea what that is.
Okay.
I mean, the only thing it could be is like if there is an like for example, you're carrying something on top of your car, and there's weight, and that would be exerted along the y direction, correspond to a normal force or something like that. I mean, that's the only thing I could think of. That would be very strange to have a force in the y direction. Something would be pushing the car down, weight or something. I don't know.
Got it.
Yeah. All right. Anything else? Let's keep going then. We got a problem, right? I know you're saying enough with these concepts. Let's get the calculator out, right? Let's exercise our math skills here. And I agree with you. I think that's what we do at this point. No, we're there. Here we go. Here we go. You want the math, you love the math, please. Don't lie and don't be coy. All right. Here's a static equilibrium problem. A traffic light. Okay, let me go to the picture first so I show you this. Here's the picture. Okay, these are my top-notch Microsoft Paint skills here. So a traffic light of mass 15 kilograms hangs from two cables to a support. The cables make angles 70, 37, and 53 degrees with respect to the support, as you see in the picture. Now, we want to know what the tension in the two cables are. So what's going on? What is our object? When you solve these problems, you may have to go all the way back to force identification, if need be, but you first make a decision about what is the object. The object is the traffic light. What's the environment? The environment are these two cables that are in contact with the traffic light, and that's all. We're given the angles that these tensions have with respect to the ceiling here, and we're going to have to incorporate that eventually into how we determine the direction of the tensions. So let's look at a picture now. I'm going to draw a free body diagram of the traffic light. I drew a coordinate system of x and y, and I'm drawing gravity to be straight down, which it is. Then I have a tension that goes up and to the left, and I'm calling that tension 1. Now, notice what happened here is my coordinate system is centered on the top of the traffic light, sort of like this. Oh my gosh. Just look away. Just look away and discuss. All right, let me try that again. Oh my gosh, I'm gonna delete that when I edit this video. How embarrassing, I can't draw a line. All right, try this again. There's my coordinate system, the same coordinate system over here. Now notice some things about my angles here. I have a tension going up this way. That's how it's pulling. This is how it's pulling. Okay, gravity's going down. But I put all of that over here. Now notice that the angles that are given, I believe the fancy term for this is alternate interior angles. If this is 37, then this is 37 down here. Up here 53, then this one over here is 53. Okay. Here we go. Now, once you draw out all the forces and the correct directions, okay, does anybody disagree with me here? Or have a question, not disagree with me. How about this? You can't disagree with me. Okay, you can't do that. I'm right, whether I'm right or wrong. Second, do you have any questions about this? Anything unclear about this? Joking about the first part. I make mistakes all the time. It's kind of ridiculous, but is this clear, this free body diagram? Anything unclear about it? How do you feel about it? Do you feel good? Does it feel scary? Is it strange?
Can you explain how to get the two values of T1 and T2?
You bet. Well, I'm not there yet. I'm just talking about this picture I drew. I want to make sure
Okay.
everybody's on board with this picture. I'm not at the other stuff yet. Okay. I want to make sure we're good with this picture. If this doesn't make sense, we need to talk about it. Okay. I'm assuming we're all good now.
So, for when you find the x value, the total force in the x value, do you always use cosine, or would you ever like?
We're not there yet. We're not there yet.
Oh, okay.
Hold up. Don't get ahead of me here. Why would the same angles... Oh, by the way, it's a coincidence that these angles add up to 90. Just FYI. Total coincidence. That's not related to the... It's just a coincidence. Well, if you feel dead inside, it's probably not physics doing that. Sorry. It may be like the fact that we're in a pandemic, you know. I don't know. That may be more responsible for it, to be honest, but I don't know. The length of the matter, does the length of the matter for the arrow matter? Does the length matter for the arrow? That's the correct sentence. Yes, I would say it does. And I would recommend that you attempt to draw your arrows to be accurate. So for example, I drew my gravity vector going down, and the length of that vector should approximately be the combined length of the y components of the two tensions. And the x components of the two tensions should be the same length. Because again, this is a static equilibrium situation here. So now, will I penalize you if you don't do it? Sort of. If you draw a picture that is so insanely lazy and not even close to how it should look, like it's just grossly incorrect, you will miss points. But I'm not going to sit there with a ruler or anything and make sure everything's perfect here. No, no, no. But I need to see that you're putting some amount of attention, you know, to this.
So the gravity line has to be longer than the line?
Yeah, so look, I drew the gravity vector. Here, let me draw this again. So this length, right? Okay. Now that length should be the same as the combined length of these two y components that I'm drawing right here. Now, are they? I think it's pretty close. Let me stack these. Oh, here's the moment of truth. Right? Here's the moment of truth right here. Oh my gosh. Oh my gosh, it's almost perfect. It's basically perfect. Look at that. I think I actually had a ruler. So the fact that I actually had a ruler and I didn't make it completely perfect is actually makes me think that this was a really crappy job. Never mind. But anyway, that's your attempt you want to make. All right, I'm going to move on because I get to the rest of this thing here. Now, here's where the magic really happens. Here's where the magic happens. Now we're going to use Newton's second law. So you have to do your free body diagram first. Maybe even before the free body diagram, you're doing a force identification diagram. Maybe. But then eventually you get to the free body diagram. And once you have the free body diagram, now you can write out Newton's second law. You want it to work out the summation of forces in the x direction. What forces are there in the x direction? I will draw them with blue. We have T2's component and we have T1's component. And so those components are respectively T2, that's the magnitude of the vector, cosine 53 degrees, that's the x component of that. Minus T1 cosine 37, it's minus because it points to the left. T1 is the magnitude of the vector, and the horizontal component needs the cosine. And that equals 0. Why? Because we are in a static equilibrium. Otherwise, it equals ma, if there's acceleration. In the y direction, I'm going to do the same thing. I have two components that point upward, T2 sine 53, T1 sine 37. Those are the upward components, which I will draw in a pleasant green, Got some spring colors in here. Nice. Down is gravity. Now, at this point, we write mg. Okay? Fg is for the picture. When I go to put the equation in there, mg is the equation. That all adds up to 0. Notice mg is negative because it points down, and I'm saying down is negative. And the physics is over. Your free body diagram is drawn. Newton's second law has been stated. The rest is just mathematics. This is a system of equations. 2 variables, 2 unknowns. Solve it by any means possible. Substitution, elimination. If you are a linear algebra freak, use a matrice, but that's kind of scary. So, but if you know that, good for you. If you solve this system, you get the following values down here. Turns out that T2 is a little bit more because it has a greater vertical component, so it's doing a little more work to support the weight of the object. But that's it. Do we solve for mg to get T2? Well, probably the way to go about doing this, to be honest, if I had to say, what's my strat to do this? I would solve for, I don't know, solve for T2 probably. Solve for T2 in this top equation, plug it into equation, the y equation down here. And then the only variable would be T1, get T1 and then go back and put it in. But you know, it's just a simple linear equation, set of linear equations. You know how to solve those. You know, substitution, elimination, matrices, whatever you want to do. Your prerogative. All I care about is you get it right.
Does it matter which one's first? Like, could have we done like T1, negative T1 plus T2?
Yeah, that's perfectly fine. Perfectly fine. Just make sure that for the components, you put in the appropriate negative signs in places. So yeah, if you write the first term first, or the second term first, or whatever, yeah, there'll be a negative on that. But I typically I just automatically write my positives components and then I subtract my negative components. That's just my style of writing. But obviously, you know, rules of mathematics say that you can write them in the order you like. I believe we call that the associative property. No,
So could you go over
commutative? One of those two, whatever. Yeah, sorry. Commutative. It commutes, moves. All right, sorry. What was there a question?
Could you go over the problem again? Because I'm still not understanding how you found the values of T1 and T2.
I'm not showing any work for that. That's the thing. The physics is the free body diagram, identifying the correct forces with the correct directions, writing out the vector components in X and Y. Because the situation is equilibrium, we add them up and they equal 0. That creates a system of equations which you have to solve. I don't show any work for that. That's just a bunch of math. You guys can do that on your own. That's not the point of this problem. But if you solve the system, and you may want to do that just to verify these answers are correct, they are. But I didn't show any work to do that. So, because if I showed you work how I did this, we wouldn't finish on time.
Well, isn't there like technically 2 different variables that you're having to solve for in both
T1
these
and
cases?
T2. T1 and T2. You don't know the tensions, T1 and T2.
So how? Yeah, I guess that's what I'm trying to think of. Is like, how do you solve for 2 different variables?
I mean, do you know how to solve this? Let me show you this. 2x plus 3y. Oh, come on. 2x plus 3y equals, how about 20? And then we're going to do 3x minus 5y equals 15. You know how to solve that system?
Definitely not.
Wait.
No.
Oh, I was going to say. If you could solve that system, well, guess what? That's the same as this. It's the same thing. You got 2 variables. Instead of x and y, I'm calling T1, T2.
I see what you're saying. Yeah, it makes more sense now when you think about it.
It's just a system of equations. Linear system. Linear system. Solve it. That's all. Okay. I mean, let me just throw this out there. If you guys don't know about Wolfram Alpha, get on it. Get on Wolfram Alpha. Okay, if you don't know what that is, Google it, Wolfram Alpha. AKA does the math for you, which you better be careful with that, though. Be careful with that. Be careful with it.
So, quick question.
Yes.
So, MG is the same as
the force of gravity, which is the 9.8 meters per second squared.
The G is.
The-
The G is the 9.8. The mg is the force of gravity. So I'll need to multiply the 9.8 by the mass of the object, which I was told is 15 kilograms.
Okay. So
Yes.
I
mean,
get
the
it now.
cosines, right? The sines all have values. The m is 15, it's right up here. And the g is 9.8, never changes. So that's a constant right there.
Got it. Okay.
Yeah.
I see it now.
All right, I like the questions. That is the truth. The calculator is only as smart as the operator. That is absolutely true. I'm just saying that if you're going to use a tool to do your math for you, better make sure you know how to use it without the tool. Because the tool should only be for convenience, not to do the work for you. Wolfram alpha, if you don't know what Wolfram alpha is, you should be utilizing that. It solves every problem for you. Any derivative, any integral, any system of equations, any graphs you want, it just does it for you. But that comes at a price, right? The price is don't sacrifice your own knowledge for convenience. Okay? Anyway. All right. Now, this is an amazing problem. This is a fantastic first problem. Here's what you should be doing with this problem. Go over this problem. Work it out on your own. I would attempt to reproduce this problem without looking at it. Solve this system on your own. Put the work in to understand this. When you're done, if there's anything you don't understand about it, you need to talk to me or a classmate. But here's the thing. This problem that I just did here, you're going to do this probably somewhere in the order of 250 to 300 times in this class. I actually kept a count one time, and it was something in the upper 200s. This problem that I just did here, you're going to do this again, probably around 250 times. So, you want to know how to do this. So if there's any questions about this, if you're unclear about how this is done, obviously we'll work on that. I do have a lot more examples today, so let's just move on. I want to make sure I get done with things. Why is there people always pulling up in my house and staring at my house? I don't like that. I guess why do I care? I don't know, but why are you staring at me? I don't know why people pull up, stare. Go away. All right. Let's move on. Oh, I love that problem. Love that problem. Please. Oh, that happened. That happened before, though. I had a student a while back, kind of a weird one. Maybe slightly stalkerish. She sends me like an email. Like a few months ago, she's like, "Oh, I saw you outside your house." I was like, "Don't do that. You see me outside my house, just okay, good for you. You don't send me an email. Saw you outside your house." Like, okay, thanks. Like, should I move? I don't know. All right. Oh, this is a good one. Oh, this is so good. A ring seen from above is pulled on by 3 forces. The ring is not moving. What is the magnitude of F? Oh, this is so good. There's some dude just sitting there. He's like in the middle of the street. He's not even moving. He's parked in the middle of the street. What are you doing? I'm looking at you. What is he doing? I don't know. I don't like it. Don't like it. All right. Letter in the chat, people. Come on. D, huh? All right. It is D. It is D. Why is it D? This problem is a static equilibrium problem. That means the summation of forces in Y will add up to 0. What's going on in the Y direction? Let's talk about it. We have a component that goes up here and up here. These vectors, these 10 Newton vectors, are broken into components, right? There's a component that goes right and up, and then this one has one that goes left and up. Now the left and right components cancel out. And that's what's going on in the x direction. In the y direction, these two upward components have to add together, and they're going to equal this downward component. So the upward components themselves are 10 sine theta. This one is 10 sine theta. The one on the right is 10 sine theta. And then there's two of them, so you double it, 20 sine theta. And that's how much the bottom must be equal to if this is truly in equilibrium. The upward and downward forces cancel out. So that's why it's up here. Now the sine functions here, because of the way the angle is defined, it is the side opposite for our triangle here. That indicates the components. So that's what we're looking at. All right. Now, this is a common theme, by the way. This is like, do you see the way this is supported? This is a very common way to stabilize something in two directions. For example, this, let's go back here, right? Why do I not want to have one cable that just hangs straight down, right? Why don't I just have a cable that hangs straight down with a street light? Because then it's not a street light, then it becomes a tether ball. And that's not really good for street lights. So we put the strings at an angle here to provide support in the horizontal direction, so that if it does start to swing, it won't swing too violently, basically. So it'd rock back and forth for sure. I mean, we still have this in the AV here. If you go out, you know, west side, I think it still has stuff, like, we still have lights on the west side here that are like hanging by like cables or something. I don't know why. Well, this case is static equilibrium, and the ring was static equilibrium. Doesn't need to be static equilibrium, that's the thing. Because the mathematics, the Newton's second law, is the same, whether it's static or dynamic. The only difference between the two in terms of doing forces is, you know, if you're moving, you probably have some kinetic friction, and if you're not moving, you probably have static friction. I mean, you would identify forces differently, but the mathematics would not change, though. So
I got a question.
yes.
What if you moved, so the 10N and the 10N, what if you moved them straight out to the sides of the ring and just pulled them with enough force that the ring stayed in one place in the air? Do you get what I'm saying?
No, not really sure what you mean there.
All right, so say you have the ring and you have strings attached to the left side and the right side.
Okay.
If there's slack on the string, then the ring kind of hangs down.
Right.
But if you pull the string tight in the opposite directions, then the ring kind of just stays there.
Yeah, it does. If there's any kind of forces, what happens is this: when you pull on the sides like this, okay, say you have 1,000 newtons pull on either side. That kind of tells you how much things are going to move around, because if things are going to move around, they have to have forces that are sort of comparable to 1,000 newtons. So if your typical forces are around 100 or 200 newtons, maybe you identify that from air resistance or something like that, then having 1,000 newtons pull on either side, you're talking about a change in the horizontal forces that may vary by like 10% or 50%, which is not very much. So the thing wouldn't move around very much. And the stronger the tension you create, the less it's going to move around for a given force. It just provides more stability. That's really it. So I don't think
Got it.
Yeah.
Okay.
All right, let's move on here. All right, got a car. Let's work out some stuff. I'm liking this problem too, quite a bit. Now, the free body diagram is already drawn for us. I pulled this from the question we had earlier in the lecture, so we don't need to reinvent anything here. We already worked this one out. Normal force is going up perpendicular to the ramp, so that's in the y direction. Static friction is going up the incline. Gravity is going down. Remember that the angle that gravity will make with the y-axis is equal to the ramp angle, and the ramp angle is 20 degrees here. So here's my three forces. Normal force, static friction, gravity down. Now, this car is parked. It is a condition of static equilibrium. So what I'll need to do is, on my free body diagram, I'll need to break up these forces into components in the x and y direction. So if I look at the x direction, I have a small component of gravity that points down the incline. Right here, basically. That little arrow I drew. That arrow would be mg sine 20. mg is the magnitude of the vector that sits in the front, and the component is given by including the sine 20 degrees. That's the side opposite. That's the component along the x direction. And then going in the negative x direction is static friction, which I just put as minus Fs. We are not developing Fs quite yet. This will come later. In the y direction, normal force is up, and what's going down, and I'll show that component, the gravitational component along the y direction. This would be the cosine component, or the y direction component, mg cosine 20. I want to find the normal force and the frictional force. Fortunately, I can just solve for them individually. This is not a system of equations necessarily. Solve for Fs, I get 5,000 newtons. Solve for n, that would be from equation y. Move the mg cosine 20 over. mg cosine 20 is 14,000. So this is a matter of free body diagram, which you've already established. Right now, components in the x and y directions, and just solving for these two things, which we got off a little easy. So we solve for Fs and n, these things. So that is what's going on with this car. Any questions about this one? Okay, let's.
Wait, actually,
Okay.
did the mass even matter for this question?
Yeah, because if you look, the
Or?
map.
Oh my gosh, yeah.
Yeah,
I
you'll need
forgot.
it. Yep.
Okay. Thank you.
Yep. Yeah. Yeah. All right. Push it on. Push it on. All right. So to summarize what we're doing when we do Newton's second law, we have a free body diagram. We have an object. We have forces that act on the object. We sum up those forces in the x and y direction, and that gives us an F net. Now, if it's zero, because the object's in equilibrium, well, the acceleration is zero. But in the situations where F net does not equal zero, we will set F net equal to ma, and then when we divide divide F net by m, that gives us the acceleration vector. Once we have the acceleration vector, if need be, we then jump into the kinematic world and solve problems from there. But the kinematics we did before, we're still going to be doing that stuff. But what will now happen is we have a first step, and the first step is a Newton's second law issue. Then we get an acceleration, and then if need be, we go into the kinematic world and solve something there. We have a free body diagram already done for us. Already done. So we don't really care about what's going on in the problem here. We just kind of care about, the free body. So I've done a little work for you here. We don't have a scenario. We just have a free body diagram. We got to work with that. The idea, though, is that this object is experiencing an acceleration, though. It is experiencing an acceleration. So let's go ahead and do it. All right. I'll need to sum up my forces in the x and y direction. Now, normally in your problems, right, you're given a scenario, you draw a coordinate system, you draw out your forces in your free body diagram. We already have a free body diagram, so we can skip that part. Now we just need to look at the forces in the x and y direction. Now, the object accelerates in the x direction, okay? It says determine the acceleration of the object and how fast it is moving. Now, how did we know that? Well, it's implied by the problem, but also if you add up all the forces in the x direction, you don't get zero. So that tells you something too. So anyway, 5 is going up the incline. So that's a positive 5. We got a 1 going down, so that's a negative 1. And then we have gravity, which has a component that's down the incline, which I will show you with this little arrow here. And so that is going to be 3 sine 20. That's that component. 3 is the magnitude, sine 20 is the side opposite. Now, that equals not 0. This object is accelerating, so we said equal to m a sub x. Now, the y direction, 2.82, positive. We have a negative component for gravity here, 3 cosine 20. Now, if you work out those numbers, you do get a 0 there. Okay, yeah, this object is not accelerated in the y direction. Okay, so we can set that equal to 0, but I mean, you don't have to set equal to 0, just do the math, it's 0. So we want to solve for acceleration here by dividing by the mass. So we get that, and we get 1.486 dot, 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 dot. That's what my calculator says. We have our acceleration now. So we're done with forces, and we jump into the kinematic world. And so I want to know how fast does it move in if these forces act on the object for 5 seconds? So the equation I'm going to use is just equation 1. The object is at rest to begin with. I guess I'm assuming that. I'm assuming we're at rest to begin with. There's nothing that tells us we are, but nothing that tells us we're not. So I'm going to go with we're not. I mean, we are. We are at rest. And then the final speed after 5 seconds is simply going to be the acceleration times the time. This is equation 1. And I get 7.4. So assuming we are at rest, after 5 seconds, all these forces are going to act together to produce this acceleration, which will allow us to travel 7.4 meters per second after 5 seconds. So in this problem here, we didn't have to set up the free body diagram, but we had to write out Newton's second law. And because there was an acceleration, one of these is not set equal to 0. We solve for the acceleration, and then we work out a kinematic problem. So that's what we did.
So in this case, because it's not equaling, or it doesn't have like an equilibrium, it wouldn't be equal to 0 for at least the f of x?
Well, I mean, look, all the forces in your x direction, there's no variables here. So you just work out this number. I mean, this number is what? I mean, it's not 0, put it that way. If it's not 0, then clearly you have to have some acceleration.
Okay, because I think what I was thinking is that you would set them equal to 0, but in this case, because there's not a variable that you're solving for, it makes sense that you just add them up and then get the actual.
Exactly. Yes. When you have a variable though, and you know you have a equilibrium, then you can go ahead and set equal to 0.
And then you're multiplying mass times the acceleration in the x direction?
Yes.
Okay.
That's just Newton's second law, right? So the summation of forces in the x direction have to equal ma. In the x direction, summation of forces in the y direction equals m a sub y, and so on.
Oh, okay. Oh, and that's why you have a sub x, because you rewrote.
Yeah, I mean, the idea is this. This is Newton's second law, right? It's vector f. Oh, come on. Let's not be. I actually have to do that. Newton's second law is vector f equals m vector a. Now, in order for two vectors to be equal to each other, their components need to be equal. So that's what we're doing here. We're saying let's take the x information and make it equal. Let's take the y information and make it equal, and any other directions you may have. But ultimately, this is Newton's second law right here, but that requires you to make sure that the components are equal. So, all right.
Real quick, and then so the 5, the -1, and the 3 sine 20 degrees and all that, those are all newtons. And so that explains why when you divide it by the mass, you get meters per second squared.
You bet. That's correct.
Okay.
It's a kilogram meter per second squared.
Is a newton.
Kilograms give you units of acceleration. You bet.
Okay. Got it.
You bet. All right. I got a little bit more time. I'm not going to get through everything because I was yapping a lot about the exam, but that's okay.
I did have one more question. When you get 2, that's supposed to be represented as the mass, right? You divided it. Did you convert that? Because I thought the mass of the car is in. Oh wait, no.
The 2's down here. I divided.
Yeah.
Right here. Yeah.
Okay, it's because I was looking at the car example for some reason, not this. But yeah, now I get it. So you use like the actual mass of the object, and then that's how you get the. Okay, sounds good.
All right, the last topic here for this lecture is on the concept of weight. And weight's a tricky concept, mostly because the term weight is very frequently used incorrectly. When people refer to weight, they typically mean your gravitational response when you're motionless, like when you stand on a scale. But ultimately, weight is your response to gravity in whatever situation you're in, whether it's equilibrium, acceleration, whatever. So, in the example here, they're showing a scale where you can hang things, a spring scale. And what that does is the spring is calibrated appropriately. You place an object on the spring there, the weight pulls down, it makes the spring stretch out a certain amount, and like I said, it's been calibrated and it will read a certain number of newtons, for example. And we would call that spring force the weight of the object. Okay, it's equal to gravity, but in this situation, it is measuring the response to gravity. For something like a bathroom scale, it's basically like a normal force. We're going to call it a spring force in this context, but you can certainly call it a normal force too. In fact, I will typically call it a normal force. Generally, your normal force is your weight. It's your response to gravity. So in the situation here where everything is at rest, though, it just so happens that the spring force and gravity are equal to each other. So spring force is going to be equal to mg. And then we can say that the weight, which is really what the spring force is equal to mg. Now, in this question here, astronauts takes their bathroom scales to the moon, where gravity is 1.6 meters per second squared on the moon compared to home at Earth. The answer here is C. Her weight would be less. Since g is less, her response to gravity is going to be less because there's less gravitational acceleration on the moon. Her mass, however, does stay the same. This is another confusing part about these two, is that mass is measured in kilograms, where weight is measured in newtons. If you have the imperial system, we're talking about, pounds. Pounds? Well, we don't use pounds. Let me just put it that way. We really just don't use pounds. But when they get confused is people a lot of times use pounds to explain what mass is, but it's really a weight. Okay, in the imperial system, mass is given in slugs? I think it's slugs. Slug, mass, slug mass. Yep. It's I don't know, slug, whatever. Next question. We have a 50 kilogram student. That means the gravitational force on them would be 490 newtons. It's 50 times 9.8. It gets in a 1,000 kilogram elevator at rest and stands on a metric bathroom scale. As the elevator accelerates upward, the scale is going to read what? Think about this for a moment. The answer is A. So you would say that this person's weight is greater than 490. Because if the elevator is accelerating upward, what is the scale really doing? The scale, if I had to draw a free body diagram of this, would look like the following here, of what's occurring here. Now we know the acceleration is upward, right? And we know there's two forces on this object. Gravity going down. And I don't know why that line's there. And the normal force going up, but the normal force is got to be much larger. Not much larger, just larger, right? Because if the F net, well, acceleration is upward, so F net is upward. That means normal force needs to be bigger than gravity. And you experience that too. If you're in an elevator, right, as soon as it starts to go, you feel a little heavier at first. Because the normal force, the ground or whatever, with a scale here, whatever you want to call it, is really responsible for a couple things, right? It's responsible for supporting your weight, but then it's also responsible for accelerating you upward. So the normal force will need to be a little bit bigger than gravity to do that. Okay. Now, let's look at how the Newton's second law is going to look here. So in the example, we have our person standing in the elevator, got a cable going upward. We're going to treat just the person as the object here. So what's happening here is if we're accelerating upward, we have our spring force, which you can also call normal force. I like to call it normal force, but spring force would be fine if we were talking about the spring scale. Going up, gravity is going down, and accelerating upward, so we're going to set that equal to ma sub y. So that's Newton's second law for that situation. Now, the spring force is going to be the reading on the scale, and that's what we're going to call the weight. So if we solve for that here, we see that we get mg plus ma sub y, and we can factor out an mg from this, and we have this nice little expression here. Now this expression kind of tells you how your weight varies with acceleration, right? So notice there's an mg in the front here. If there's no acceleration, then you get a 0 here, and then the weight's just equal to mg, which is true for equilibrium. But if you're accelerating upward, for example, this would be a positive value for a sub y, which you're then adding to 1, so that means your weight's going to be larger than mg. If you're accelerating downward, then this would be negative, and that means you're going to do 1 minus a number, which means mg, your weight's going to be smaller than mg in that situation. And that would occur in a situation, for example, where you're going up the elevator, but then the elevator is starting to slow down. And what happens is the spring force or whatever will weaken, so that gravity kind of takes over and slows you down. Your F net is downward, acceleration is down, and your weight will be a little bit less, which again, same thing. If you're in an elevator, you get to the top as you're going up, you kind of feel a little lighter when it hits there, just temporarily. Okay. Now, with astronauts, they're weightless, right? Because they're in orbit, and their acceleration is equal to g. It's downward, negative g. So that means this whole term is 0 here. That means they have no weight. There's nothing to support themselves against gravity. They're in free fall, right? They're always falling as they're in orbit. So that results in weightlessness for them. Okay. By the way, this equation, just be careful. This is not an equation that we are developing that we're going to be using in this class. This is just something that happened to come out of Newton's second law. But it's not a standard equation like kinematic equations are or something like that. This is just a one-time use thing. I don't recommend using this for anything else, you know. Okay. Question for you here. We got a 50 kilogram student, gets in a 1,000 kilogram elevator, at rest, stands on a metric bathroom scale. Sadly, the elevator cable breaks. Oh no. What's the student's weight during the few seconds it takes the student to plunge to his doom? Well, maybe they make it. So we shouldn't be presumptuous with the doom thing, you know. But if the elevator cable breaks, then their acceleration would equal gravity, and they would be in free fall with the elevator, so they would have no weight. Your feet would, I wouldn't say lose contact with the ground, but there'd be no more normal force anymore. You're effectively not in contact with the floor anymore. Unless for some reason the elevator doesn't fall as fast as you, then there would be a little contact, but you know. Last example here. Gregory, whose mass is 80 kilograms, is in the elevator descending at 10 meters per second. Takes the elevator's 3 seconds to come to a stop. We want to know Gregory's weight before the elevator starts braking, and what's Gregory's weight while the elevator's braking. Okay, fantastic. Let's do it. All right. Before braking, you're coasted at a steady 10 meters per second. There's no acceleration. Therefore, the normal force, which I'm calling normal force, in the examples they call it spring force, same thing pretty much, is equal to mg. Your normal force is your weight, so 80 times 9.8 gives us a force of 780 newtons. That would be Gregory's weight before the elevator starts to brake. Now, as the elevator brakes, you have a free body diagram that's going to like this thing on the right here, where your normal force is going to be larger than gravity going down. Because if the elevator is starting to come to a stop, there has to be acceleration going upward since your velocity is downward, right? So when I write out Newton's second law for this scenario, you have normal force up, mg down, and the acceleration would be equal to this would be equal to ma sub y. We are experiencing acceleration that is upward here. So normal force is your weight. So I'm going to solve for that. That's equal to m times the quantity g plus a sub y. What's a sub y? Well, we'd have to work that out. In 3 seconds, we go from 10 meters per second to 0. So if I do a little definition here, right, the definition of acceleration is delta v over delta t. That's 10 meters per second in 3 seconds. This is an acceleration of 10^3 meters per second squared. So that will go in for a sub y here. And I add these up, multiply by 80, and notice that my weight is larger, right? You would feel heavier in this situation as the normal force is pushing on you harder than it normally does because it's trying to support your weight and it's trying to slow you down. So it's kind of two purposes there. So we have an experienced larger weight here. But that's it. So be careful with the concept of weight. When you're in equilibrium, your weight is mg. But if you're accelerating, it's different. And you really want to analyze what your normal force is doing to determine what that weight's going to be. All right, that's the end.